one of the reasons I wanted to talk about neural networks now rather than later on throughout the year is that there's all this new craze that everybody's about deep learning and machine learning is taking up a lot of the data science discussion. So I thought it would be a good time to talk about neural networks and get you all used to how to get the most out of JMP, which is I find the neural networks to be an underutilized tool in JMP. So what we'll do today is I'll give you a quick introduction of what the neural networks are, how they work. And we'll work through a simple example of I think is a very good use of neural networks, and it kind of shows its advantages compared to other type of modeling tools. And once we take a break, we'll look at two case studies. One is about from a healthcare perspective. One is on how to identify if the mushroom is edible or poisonous. And that being said, let's get started with the neural networks. And I'm going to try to go through this presentation without talking about brain or neurons to make this more accessible to everyone rather than going into high math details and talk about the construction of the neural networks in historical perspective. So neural networks are used in a whole variety of areas, from predicting if the river will be flooding this year or not, to very complicated financial applications on detecting the credit card fraud, or to approve someone for a credit card, or to see if there's to identify corporate credit ratings, predicting bankruptcies, using on the stock market. So there's a whole wide of application areas for using neural networks. The main advantage of the neural networks is that it is extremely flexible. You don't have to be limited to using a linear model or a decision tree type of model or a formula that needs to be built in a chemical or physical settings. It starts with a very basic assumptions, very simple formulas, and then builds a complicated network of models. Eventually, they will help you identify what's happening in your process and in the data set that you're within. This random data set, there's a spiral in different colors. And if I were to use the regular modeling tools to identify not only if there's a spiral in this picture, but also which color it is and which layer it fits to, this will be a very challenging problem. However, this kind of problems are they're easy for neural networks. They can identify each of these layers in the data. So with all this, I'll just open the data set to give you an idea of what this looks like. So I'll go to my graph builder, and I will put my x-axis on my x values and y values on my y-axis. And by looking at the first sight, it's hard to, now that you know there's a spiral in there that you can see it, but at the first sight, even for a human eye, it's hard to identify there's a spiral here. If I take my k values and color it, and also size it with that, now you can identify these spirals, and they're different colors, different layers. So we'll go through, while explaining neural networks, how they work, we'll go through how to identify each of these layers on this picture using the neural network tool. So let's take a step back and talk about what neural networks are. What neural networks are, they're self-learning machines. What they do is they start with randomly selected simple assumptions, and they build basically multiple layers along the way. And each of these layers, so we will talk about these and how they come into play in using JMP. At each of these layers, neural network use simple activation functions. I'll talk about these in a second. And at every point of these nodes, each of these are called nodes. At each of these nodes, the model compares our results coming from randomly selected simple assumptions to how they compare to our output, and then pick the better ones and discard the rest. And looking at how close I am to my output, basically at the end, it makes changes to my random assumptions in the beginning, and random assumptions that I made in the beginning. And by basically learning from each of its mistakes along the way, it builds a self-learning algorithm to identify how each of my inputs relate to my output. And that being said, what becomes important here is that, so what are those activation functions, right? Activation functions there are three different activation functions that JMP uses. One is the hyperbolic tangent function. So it normalizes the value of the variable from -1 to +1. And it's used to identify where is the threshold value in this particular variable that a change in this variable becomes important in my output. And the linear function is, we're all familiar with. We're basically trying to build regression type of model, linear regression model. So basically assigning random weights to each variable and then building a linear combination of these. And the Gaussian function is basically to look at the spread of those variables about the point that I select, about the weight that I select for each of those variables. And it's a mouthful. Let's look at this as a picture ways. In the picture, see how these variables look like. So what I have here is the first one is my hyperbolic tangent function. So this talks about at what point is the relationship is actually changing with my input, and at which points those are basically not relevant at all. And so this is a linear activation function. So we can basically see there's a linear correlation between my input and output variable. And the Gaussian function, and you see most of my data points are centered around where basically the change is actually occurring. And it gives me the spread of these data points. And you might find in the literature Gaussian functions are also used as radial basis functions, and they're also used in the support vector machines as well. So if you hear those names in the literature, they refer to certain forms of Gaussian functions. Another way to look at this is that this is on the left, I have a static picture, and you can see on my x variable, if I change my x variable, you see my hyperbolic tangent value here is not necessarily changing until I hit a certain point. Then the change becomes incremental as I change my x value. After some point, it's not changing anymore, and you see it's kind of limited to 1. And you can also see how it's changing for my linear variable, and you also see the spread of my expected weight and how it changes with the Gaussian around it. So what I have here is just one of those layers. And if I go back to this picture here, so each of these layers here, at each of these nodes, what I'm comparing is one of hyperbolic tangent or linear or the Gaussian function. So what I'm looking at here is the value of each intermediary variables. And these are also your nonlinear principal components. And if you remember from multivariate analysis, WebAccess, or in your previous studies, when we're building principal components, we're building composite variables that basically explains the variation in a different dimension. And it's extremely helpful for variable reduction as well. So basically going through each of these variables, I'll be able to identify the best ones. And every single time, every single point I come back to a node and compare to my output, I'll be able to learn from it and make changes and build a better model, basically. And I think this is a good time at this point to look at what the neural network platform looks like. So what it is under Analyze, Modeling. There's an option for Neural. And Gail mentioned earlier is that if you have JMP, you will be limited to just one layer of Gaussian neural network. But with the JMP Pro, we'll have more flexibility. So let me just walk through this for a second here. So I'm trying to identify each of these layers, which are my K values, and I'll put them in my response. And I will put the only inputs that I have are my X and Y values, put my X factor. And I also selected a validation data set, and I can put into my validation. But for now, let's just go with it for demonstration purposes. And then say, OK. What I have here is that we talked about each of these layers, first layer and the second layer. So basically, going back to my picture, so this is my first layer, and this is my second layer. Second layer are closer to the inputs. And I can identify how many of each of these nodes, how many of these nodes I want to build. What I will do is I'll just go and so you can specify how many nodes that you want to put on each layer. There is not a hard rule on how many nodes you should identify. It's more of a trial and error type of thing, and it's also an art depending on your data. You will have some flexibility how complicated you want this model to be or how simple that you want this model to be. But it's a good start to have, let's say 3 nodes on each of these layers and each of those functions, and let's see what we come up with. And the next thing to look into it is in the platform is the boosting methods. Boosting refers to basically learning from each of those mistakes. I know I keep repeating this, but I think it's worth repeating. Neural networks are self-learning machines, and you want to give them a chance to learn from its mistakes. And in the boosting section, what we do is we need to tell the algorithm how many times do we want to make mistakes, how many times do we want to try. And I'll say, you know what, I want you to try 10 different times. Start with some random values, try to see how it compares, go back, that's my one visit, and then change the weights and go back and try it again. So when I say change the weights, then becomes how much to change the weights in each time I try. And that's where the learning rate becomes important. And again, there's no hard rule for the learning rate, but as a rule of thumb, I would go with 10% learning rate. What this means is that every time I make changes to my weights, how much change is allowed. If you make the learning rate higher, it's going to hit the maximums pretty quickly, and then you will probably miss your global model. You might end up with a local model applicable to the portion of the data you're looking at. If you make this too small, then it's probably going to take too long. And when I mean too long, I'm talking about a couple of minutes rather than a few seconds to build a model. So let's leave as it is 10 and then learning rate to be 0, 1. And the next option on your screen is the fitting options. This is basically while we're fitting the model, what kind of penalty method that we want to use. Because the chances are my initial guesses for the weights is not going to be applicable. And how do I go about changing these weights? And you have a couple of options. One is the squared weighting, other one is the absolute weighting, and the weight decay. Squared weighting is basically very similar to the linear regression, looking at the squares of the distances from the predicted, and then decide if you want to reduce the weight on this or increase the weight on this particular variable. The absolute decay, the absolute penalty or the weight decay penalty is basically, instead of using the squares, use the absolute error from your predicted point to your actual point. And this is helpful. The squared method is helpful if you expect all your variables to be important on your output. And the absolute and weight decay method is helpful if you know only some of your variables are impacting your output, but you don't really know which ones, and the algorithm is going to help you find out which ones they are and how they impact your output. Another option here is that the transform covariates. I strongly recommend you check that whenever you're using neural networks to build an exploratory. The reason you're trying neural networks is your regular linear models didn't really give you what you wanted. You came up with, maybe, for example, if you're in a business that measuring yield, if you build a model assuming normal distribution, you might end up with 110% yield, which is not necessarily correct. So if you believe that your data is not normally distributed, you might want to check the transform covariates option. What that will do is it will go through each of your variables, and if it's not normally distributed, it will build a transformation to create a normal distribution from your variable, and it will use that to build a model. And in this example here, I have an option. So a picture I can see here. You can look at it here. From my data set, I looked at the distribution of my data, and I want to jump to find the best distribution of my data set. And if I look at my x variables, and I can see it's not necessarily normal distributed. It's a normal 3 mixture, and then other types of distributions here. And if you ever want to do this yourself, if you put a variable on distribution under the red triangle, there's an option for continuous fit. If you know what type of distribution you want to fit, you can select it. But if you select all, JMP will give you all available distributions and find the right one for you. So what happened is neural network transformed this for me. Now I can see a nice and normal distribution, and it says if I take the log of this x values, which is the G log distribution, it will be normally distributed. So I don't have to go and do this before I build a model. JMP will do that for me. Go back to, so check the transform covariates option, and then I will say, and it will, one more thing that I want to talk to you about, I forgot to mention. Just let's just be done here. It'll take a few seconds. So it has a model for me, and it tells me my confusion metrics because I'm looking at categorical variables, and gives my R-square values. And we'll talk about this output screen in a second. One thing I forgot to mention is that I didn't talk about this number of tours. But number of tours come into play is that every time you run a neural network, we talked about earlier, what happens is we start with a randomly selected assumptions and feed these assumptions to activation functions, pick the better ones, and then on. Every time you start a neural network, it will start from a new random number. So even though you use the same settings every single time, if you run it again, you might get a different result. Different meaning that not necessarily once you get 10% R-square, once you get 80% R-square, it'll be more like, 72% versus 74%, but it's not going to be exactly the same. You can get around that by either using a script and set the random seed, or you can have a fairly large number of tours, let's say 19 or 20. So what will happen is JMP will build a model using the random start and go back and do it again. Go back and do it again. So every time it restarts, it will have a new random number. So by doing that, you're basically finding the best of this 19 or 20, however many tries that you have. So next time, if you run it again, it will be the best of those 19, 20, and you're more likely to get the similar result as you did in the beginning. Or you can always use this to set the random seed, so every time you run it, you'll get the same results. So what I mentioned to you earlier is that your neural network starts with random, some simple assumptions, and it will go through each of them to find the best selection for you. So what I did is I saved all those random starts, and each of these, and I wanted to show you how neural network goes through each of those selections to find the best fit that I'm looking for, basically. And I wanted to show in the graph builder and color them by each of those layers. So in the first layer, it's dividing my full space into two, and let's see if it can identify it. So it will compare the results to output, and then 2 and 3. And you can see the progression of the space it's exploring without me doing anything about it. So you can look at these, and I will just play it so you can see how it explores the space. So it's go through different options, and towards the end, you will be able to notice the spiral points that's selected. See if I can stop it at that point. Eventually it will be there. And you see that I identified some spirals. I'll just go through this slowly so you can see. So there's one there identified, and try something else, and it's way off, so it will stop. So that's how the learning works using the neural networks. And I will show you the final, what it looked like at the end. It's my graph builder, my X values, and Y values. And let's color them by original layers. Let's remove the smoother, and also size them with the original so they will show up. So at each of these values here, these are my original, and now we'll look at to see the clusters predicted by neural model, and you see they are pretty good. It's only missing 4 or 5 data points. And this would have been a very challenging task for either a linear model or even decision trees. I mean, I have these results, I can show them to you. But the point here is that neural networks are extremely flexible and very easy to build, and it will more than likely give you what you're looking for, and it's not really that scary as people make it sound out to be. And it's not a black box. We will look at another example later on, and you can see the effect of each of those variables. And once you understand these nonlinear principal components, you'll be able to use and explain neural networks to anyone, basically.